looking here at section 10.3, composite functions. Composite functions are another way that functions can be combined. In order to create a composite function, we evaluate the range of the first function. This range becomes the domain for the second function, and so on. Mathematically, this is written as f of g of x or f of g of x. So I need you guys to be very clear on this. When there is the open circle, that we say that is of. So this open circle is f of g of x. Now when you're looking at this, there's an inner function and an outer function. So the inner function is the one you evaluate first, and you work your way to the outside. So, for example here, if you have f is root x and g is 2x plus 3, then we're going to find f of g of x. So what that means is I'm going to insert the g of x into the f of x, because g of x is my inner function. I'm going to take that, I'm going to put it into my outer function. So it's kind of like this. X is the value in g of x, and then if I put g of x into f for the x, we end up with square root of 2x plus 3. So again, you're putting your inner function into your outer function. So just make sure you understand that the order is important for this. Having f of g of x and g of f of x are not the same thing. You evaluate the inner one first before plugging it into the outer one. So in the second one, you have to evaluate f of x first before plugging it into g. Okay, let's try example 1. Example 1 says we have 3 different functions. We have f of x, g of x, and h of x. First, we're going to determine f of g of 3. This means I'm going to start by calculating g of 3. So I'm plugging 3 into the g equation. So this is 3 plus 4. So g of 3 equals 7. Now, we're going to take that 7 and we're going to plug it into our f equation, because f is the outer function. So when I plug in 7 into the f equation, we get 5 times 7, which equals 35. So my answer for f of g of 3 equals 35. Alright, so part B here, we have g of h of negative 2. So we're going to start by plugging negative 2 into h. So h is 3 times negative 2 squared. This is really 3 times 4, so 12. So h at negative 2 is 12. Now what do we do with the 12? Plug it in for g. Yeah, plug it in for g. So now we're going to evaluate g of 12. I should have put 12 in there. So g of 12 is 12 plus 4, so 16. So our answer for g of h of negative 2 is 16. Alright, I'd like you to please try C and D on your own. So please check your answers for C and D with that on the board. Let's try our next one. So if you're given a graph, here we have the graph of f of x is the absolute value function, and g of x is the red linear function. So if I want f of g of negative 4, that means I'm finding my answer for g at negative 4. So at negative 4 here, g is 0. Okay, so what this means is that then I'm going to find f of 0. Because I take my answer for one and I plug it into the other one. So g at negative 4 equals 0. Now I'm going to find f at 0. So at 0, f is 2. So my answer for that whole thing would be 2. So again, you're finding your answer for one and then plugging the answer into the next one. Let's try B. F of g of 0. So let's start with g of 0. 2. G of 0 is negative 4. Yes. So that means I'm going to plug negative 4 in for f. So negative 4 for f. What's the f value at negative 4? Positive 2. Great. So my answer here is positive 2 as well. Let's try our next one. F at negative 2 is what I need to calculate first. So at negative 2, what is f?
0.
At negative 2, f is 0. Yep. So now I'm going to find g of 0. And at 0, what's g?
Negative 4.
Negative 4 right here. Good.
So we look for it on the x-axis.
So this is example 2 on your handout. Now we're going to find the equations and look at restrictions of these functions. So first we're going to determine f of g of x. So that means g of x is my inner function, and I'm going to put g of x in for f in my, or in for x in my f function. So that means that f of g of x is going to equal the square root of x squared minus 1. So what happened here is, again, g of x was x squared, and I'm going to put x squared in for x in my f function. So I'm trading the x squared into the x position of my new function. Okay, so for our second one here, we're going to be putting f into g. So this time, okay, we're not going this way. We're taking f, which is root x minus 1, and we're putting it into x in my g function. So my new equation for g of f of x would be root of x minus 1 squared. Because again, what I'm doing is I'm taking the root x minus 1 and I'm putting it into the x spot in my g function. So next we're going to state the domains. The ranges can only be done if you're given a graph. So we'd need to use Desmos or something to graph this if we wanted to find the range. Now the domain, we can look at each of these separate domains. So for the first one, the domain of the root function for f of x is going to be x is greater than or equal to 1. And g of x is just a parabola, so the domain is an element of reals. Now these domains, though, do not just take what's common. We actually have to look at your new functions to state their domain. So the function of f of g of x is x squared minus 1. Now let's think about what this graph looks like, you guys. The graph of x squared minus 1 is a parabola moved down 1 unit. So it's a parabola that looks kind of like that. It's moved down 1 unit. When you square root a parabola like that, we did that already in our radical function unit. When you square root a parabola like this, you put your invariant points on, and then your graph would go to the outside for both. That's because down here you can't root a negative, so there would be no graph down there. So when I think about this graph, we'd say that the domain is that x is greater than or equal to 1, or x is less than or equal to negative 1. So notice how there is some similarity to our domains from above, but this domain, when you're doing composite functions, can be totally, or is not follow the same as the adding and subtracting and multiplying and dividing. We don't just take what's similar, you actually have to think about your new graph and then assess the domain. So the domain for g of f of x is going to be a little bit different. Since my equation is square root of x minus 1 squared, we do just have to look at this inner function and see where the inner function is not allowed, because if the inner function is not allowed, then the outer function will not be allowed as well. So that would be my domain for that situation. Alright, so example 3 is working backwards. I do think these ones are fairly simple. It should be quite obvious in each question. So this one's saying that h of x is f of g of x. We're going to determine f and determine g. So we're given h. Now, when I look at this, there seems like there's something out of place. What seems out of place in this question?
The things in the brackets.
The things in the brackets, right? These seem kind of out of place. So let's say that that is our inner function. We're going to call that g. So g of x is going to be x plus 5. Now, if I put that in to f of x, that means f of x would be the same thing, but instead of having x plus 5's in there, we just have x's in there. Because the x plus 5 I would put in for the x's. So that means f of x would be x squared minus 2x minus 3. Because again, if you look, if I trade the x minus 5 in for my x's, we'd end up with h of x. So here for h of x, we have the square root of x squared minus 3x plus 2. So I'm looking here, my inner function would be that part that's under the root. And if that was what I plugged in for x, that means my outer function is just the square root of x. So again, what happened here is I would have taken x squared minus 3x plus 2, and I would have plugged it in for x in my f of x equation, giving me h of x. Alright, let's look into example 4. Example 4 here is a word problem. We have a spherical weather balloon being inflated. It's got a radius in feet. It's given by the function r equals square root t, where t is the time in minutes. So again, it's just talking about inflating a balloon and how long it takes compared to how big the balloon is. Now the volume formula for a sphere is 4/3 pi r cubed. But we don't want this volume as a function of radius. We want the volume to be a function of time. So what can I plug in for r so that now we have time instead of radius? Square root t, exactly. So we can say that this is 4/3 pi square root t cubed. That's exactly what function composition is. I took a function and I put it into another function. So I took the function of square root t and I plugged it in for r in my other equation. Alright, so for part B, we're going to put 4,000 in for v, and then we're just going to solve for t. So to solve this, we've got a little bit going on here. I think what you could do is go 4 times pi divided by 3. You could probably figure that part out first.
And then,
which gives us 4.2 and then square root t cubed. So let's then divide that 4.2 over so that all we're left with is that t, or that square root t cubed. Okay, so first we may want to get rid of the cube, but in order to get rid of the cube, we would need to cube root. So when we cube root 952.4, what do we get? About 9.84. But then we have to get rid of this square root, so we'd square both sides to get rid of the square root. So 9.84 squared should be approximately, I'm going to put a squiggly equal sign in here because it's a little bit off. I got approximately 97.
Yeah.
So approximately 97 minutes to fill a volume of 4,000 feet cubed. So we need to take some time for this, so we'll take the next little while to work on this assignment.